In this video, I'd like to talk about the powers of complex numbers. And I've copied down the formula for multiplying two complex numbers when they are written in their polar form, where remember that polar form just represents the complex number as a product of its magnitude or its modulus multiplied essentially by its direction, where this angle is measured relative to the positive real number axes. And when we multiply two complex numbers, we multiply their magnitudes and we add their angles. And what I want to focus on for this video is what happens when we take a complex number and raise it to some exponent. So let's say we have a complex number z and we raise it to some power, which we can call n. Can we come up with a formula that describes what happens? And to approach that, we essentially just need to think about what happens if we take a complex number and multiply it by itself. So let's say that we have z1 and we multiply that by z1. Or we could just write it as z1 squared. And we'll use this formula for multiplying two complex numbers in their polar form, since we do have the polar form of z1. And essentially, everywhere we see this green z2 or theta 2, we will just replace it with either the magnitude of z1 here or theta 1 here for the angle. So when we square z, we get the absolute value of z1 multiplied by the absolute value of z1, or we can just write this as the magnitude of z1 squared, and we will multiply this by the cosine of theta 1 plus the cosine of theta 1 plus I times by the sine of theta 1 plus theta 1. And we could simplify all this. Let me just make a bit more room. As z1 squared is equal to its magnitude squared multiplied by the cosine of twice theta 1 plus I times by the sine of twice theta 1. And we could go another step further. Let's now ask the question of what happens when we raise this number to the third power. Or in other words, we're taking this z1 squared and multiplying it again by z1. And like before, when multiplying two complex numbers, we multiply their magnitudes and we add their angles. So we would have the magnitude of z1 squared, which is just the magnitude of z1 squared as we found with this formula. And we're multiplying again by the magnitude of z1, that's the magnitude of this number. And we're adding the angles. We know that for the z1 squared expression, we had twice theta 1, and the angle from z1 would just be theta 1, which we'll now be able to simplify. And we have the same angle for the sine function. That's twice theta 1 plus theta 1. And we can simplify this to 3 times theta 1. And out front, we can rewrite this as the magnitude of z1 raised to the third power, since we're multiplying it 3 times now. And again, this is, if we simplify it, z1 raised to the third power. And we get the cosine of 3 theta 1 plus I times by the sine of 3 times theta 1. And at this point, we can see the pattern. If we multiply again by z1, or in other words, if we have z1 to the fourth power, then this would just be the magnitude of z1 to the third power multiplied by the magnitude of z1, which would give us the modulus or magnitude of z1 raised to the fourth power. And we would add the angles. So we already have 3 times theta 1, but we would be adding another theta 1, meaning now we have 4 times theta 1, and of course we have plus I times by the sine of 4 times theta 1. And at this point, since we can notice the pattern, essentially whatever power we're raising this to, we will raise the magnitude to that power and we will multiply the angle that many times. So we can generalize this to what happens when we raise this to the nth power. And let's say we have z raised to the nth power. We can drop the subscript of 1 if we want. This would just be the magnitude of that complex number z, its distance from the origin, raised to the nth power, multiplied by the cosine of n times theta 1 plus I times by the sine of n times theta 1. So our conclusion is that if we take a complex number and raise it to some exponent, the nth power, then we can use this formula here where we essentially take its magnitude and raise that to the nth power, and we multiply its angle n times. And we will look at specific examples in later videos, but one other way to rewrite this formula, and I might pronounce this name incorrectly, but we can write out what's known as de Moivre's formula as the magnitude of the complex number multiplied by the direction of the complex number. We can say cosine of theta plus I times the sine of theta. And if we raise all of this to the nth power, then this is equal to the right-hand side of this equation, which is boxed in orange. And again, this is de Moivre's theorem.